Hi everyone, and welcome back to the tutorial. Today we're diving into a topic that is absolutely fundamental to every map, every GPS reading, every engineering design, and every piece of survey data you will ever handle. We're talking about datum, coordinate system, and map projection. You might have heard these words many times. They sound technical, and sometimes people just skip over them. But without understanding these three concepts, your data will never align correctly, and your map could be off by hundreds of meters. So today, I'm going to explain them in a very simple and practical way, exactly how they are used in real-world surveying and mapping. First, what is a datum? Let's start by imagining we want to describe the exact position of any point on the Earth. Before we can give that point any coordinates, we need a reference model, something that defines the size and shape of the Earth. That reference is called a datum. A datum tells us which mathematical model of the Earth we are using, flat, round, ellipsoid. Where the center of that model is positioned, how that model fits the real Earth surface. By the way, the Earth is not a perfect sphere. It's slightly flattened at the poles and bulged at the equator. So we use a mathematical surface called an ellipsoid to approximate its shape. Different datums use different ellipsoids. For example, WGS-84. This is the global datum used by GPS satellites. Your phone uses it. Google Earth uses it. Adindin. This is a regional datum used in East Africa. It fits this region more accurately than WGS-84. So if you collect GPS data in WGS-84 and try to match it with old national maps based on a Adindin datum, your points will not line up. That's how important datum is. After we understand datum, let's move to the coordinate system. Now that we have a reference model of the Earth, the next question is, how do we express locations on that model? That's where the coordinate system comes in. There are two main types. 1. Geographic coordinate system. This uses latitude and longitude. These are angles measured in degrees. It's like saying, how far north or south of the equator, and how far east or west of the prime meridian. This is what GPS gives you directly. Something like latitude, 9.0123 degrees north. Longitude, 38.7654 degrees east. It's very good for global positioning, but not convenient for measuring distance or drawing engineering plans, because degrees are not equal everywhere. 2. Projected coordinate system. Instead of angles, this system uses straight-line measurements, eastings and northings in meters. This is much better for engineering, contour generation, and construction layout. The most common projected system we use is UTM, Universal Transverse Mercator. It divides the Earth into zones, like Zone 36 or Zone 37, and gives you coordinates in meters for easy calculation. Then we're going to map projection. Now here is where it gets interesting. The Earth is curved. Maps and computer screens are flat. So how do we convert the curved Earth into a flat surface? We use a process called map projection. Think of it like peeling an orange and trying to lay the peel flat on the table. It won't be perfect. It will tear and stretch. That is exactly what happens when we project the Earth into a flat map. That's why every projection introduces some distortion, either in area, distance, shape, or direction. So projections are chosen based on what we want to preserve. For example, Mercator projection preserves direction, good for navigation. Transverse Mercator, UTM, preserves shape locally, ideal for surveying. Lambert conformal conic is good for countries that stretch east to west. Now, let's connect all three together. To accurately locate any point on Earth, you must define datum, the Earth model, map projection, how we flatten that model, coordinate system, how we write positions in numbers. For example, if I say, UTM Zone 36N, datum WGS-84, that tells us everything we need to correctly position a point. But if I only say easting equals 500,000, northing equals 999,000, without telling you the datum and projection, that number is meaningless. It could be anywhere in the world. This is why surveying engineers and GIS professionals always define datum and projection before importing or exporting data. Real-world example. Imagine you're working on a construction project in Ethiopia. If you use Datum, a Dindin projection, UTM zone, 37 north, you will get coordinates in meters that match national grid systems. But if you use Datum, WGS 84 projection, UTM zone, 37 north, the coordinates will be slightly shifted. If you mix them, your design will not match the site. So understanding datum and projection is not just theory, it's practical and critical for accuracy. Please consider subscribing to this channel and watch many other videos in other language options also.